So when it comes to addition, if you think back to when we talked about addition of whole numbers, we had our set model. We don't often talk about sets when it comes to fraction addition. We often talk about the area model, the number line model, and then the fraction bar model. And the fraction bar model is a really commonly used manipulative and turns out e-manipulative that we use in elementary mathematics, particularly with modeling fractions. And so the activity for today's material that we'll do on Wednesday is actually going to have you work with a free fraction bar generator maker on the Bridges curriculum website. So it's free to use, but you'll be generating fractions and you're going to be using them to model addition and subtraction. So we can use an area model that looks like this. Suppose you have a pie that's cut into fifths, and so you have 2/5, and then you later eat 1/5. Altogether you had 3/5, right? And so we can do that just by stacking them on top of each other and seeing, right, if we would take that blue one and set it and rotate a little bit on the 2/5, 3 of them would be filled. And that was just like our area model with the vertical bars. And this is really going to resurface again when we get to the fraction bar, because you're going to see that fraction bars are just a very specific way of using the area model that kind of pushes towards the number line model, but doesn't quite go all the way there. So with our number line model, 2/5 plus 1/5 is 3/5. We go over 2/5, over another fifth, we end at 3/5, and so we're good. And here's our fraction bar. 2/7 plus 3/7 gives us 5/7. Because if we take those two, stick them next to that 3, so just draw and show you what that looks like. Right, if we would take those two and move them over here, we'd end up with 5 of them that are shaded. It's 5/7. So these models are fine and dandy when we have the same denominator. Because in general, if we have a over b and c over b, if we have, for example, what was our previous one? 2/7 plus 3/7. 2, a is 2, b is 7, c is 3. If 2/7 and 3/7 are both rational numbers, they are, then 2/7 plus 3/7 is 2 plus 3/7, or 5/7. So our formal definition for addition is if we have a common denominator. Notice all 3 fractions. We are referring to same size pieces, because to add pieces together, we need to have them to be the same size. A plus c is a plus c, right? So that's our general definition for fraction addition. So 2/7 plus 3/7, I just said if a then is 2, 3 is c, and 7 is b, what we're left with is 5/7. But what happens when we don't have common denominators? What if our whole, because what this shows us is we have a whole, actually we have 2 of them. One of them split into 6, so we'll do thirds and then half. And the other's in quarters. And in this one, we have 1, 2, 3, 4, 5 of those sixths. And over here, we have 1, 2, 3 of those quarters. And we want to combine them. Well, I mean, we could just stick them together, but we have no way of knowing how they correspond. And so this is our process of common denominators. And so what I'll do is, what is the smallest number, or let's use our terminology from last week, what is the least common multiple of 4 and 6? It's 12. 2 6s are 12, and 3 4s are 12. And so what do I need to do to the 6 to get to 12? I need to double it. So let's split every single one of these pieces in half. And what do I need to do 4 to get to 12? I need to multiply by 3. So let's put each of these quarters into thirds. And now what happens when we compare these two is we no longer have unlike bases because we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 twelfths up here, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9 twelfths down here, and now we have our previous definition of addition will work. 10 twelfths plus 9 twelfths is just 10 plus 9 twelfths, or 19 twelfths. And so what does that look like? So first, we had our sixths and our fourths. And what we did is we first needed to get our fraction bars into same size pieces. I'll move myself just down a little bit. And from there, because we have common denominators, we can add them. We ended up getting 12 and 7 more, which is 19 twelfths. So this is our process for getting common denominators. Whenever we have two fractions, but notice now it's not b and d. B doesn't equal d, and let's add b and d non-zero, because that can't be true either. Oh, well, we know they're not zero. Why do we know they're not zero? I'll erase that. Because I already told you that they were rationals. And rationals are only defined if the denominator is non-zero. So we know that they're not the same, and we know that they're not zero. Then generally speaking, a over b plus c over d, ooh, that looks way too much like 2d's, plus c by d equals. And just like we did in the previous, we end up finding common denominator. In our previous example, we found the least common denominator. But here, we're just getting a common. It doesn't need to be the least. But what we have is, to get a BD in the denominator, the product of these two, this one we have to multiply by a 1 that looks like d over d. And this one we have to multiply by a 1 that looks like b over b. And here we have AD plus BC all over BD. So, that is our process for finding common denominators. We start with our parts. We work towards same size pieces. Once we have same size pieces, we can combine them, and then we end up with this product, or this sum that looks like this. So if you see this and you're like, A, B, C, D, what? Just focus on the image. We have parts, and we need same size parts to add. And so you can use fraction circles. This is another common one. And another reason that these are used is because you can actually stack them on top of each other. And I will demonstrate that the day that we do this activity in class. But so if we have a quarter and 5/6, we do that same process. We need to find their least common denominator or any common denominator. Because what we could do is every single, this wouldn't be efficient, but we could do this. That previous slide says that we want to find this as something over 24, 6 times 4. And it ends up being 6 times 1 plus 4 times 5. But why? Why is that the case? Well, let's say I take every one of these quarters and I split it into 6. So 1, 2, and now that's too many. We'll pretend I could count. Try that again. Thirds, and then halves. There we go. Thirds, and then halves. Thirds, and then halves. Thirds, and then halves. We have 24 pieces and 6 shaded. That's 6 times 1. And then here, since we already have a 6, we have to split each into 4. And now we have 1, 2, 3, 4, 5 with 4 in them. That's 4 times 5. That's our 20. 20 pieces of 24. And so that gives us 26 pieces out of 24 total. And you're like, well, that's not what this says. This says 12ths and 12ths. Well, it's 13 twelfths. Multiply it by 1. That looks like 2 over 2. 26 24ths. And so this is our least, or we can call it our simplified. P-L-I-F-I-E-D, simplified, because we used our least common denominator. But you need not. You just need a common denominator. Least makes it a little bit more efficient, not so bad, but isn't a necessary thing. Okay. So that's the gist of it. We know that addition is the joining of sets, adding things together. We know that subtraction is the taking away. Fraction addition subtraction is precisely putting together and taking apart fractions. The homework's going to give you a good bit of practice on thinking about the concept of fraction, union, and separation, but also just practice in terms of fractions in general. And so we also have our friends, the mixed numbers. So that previous fraction, 26 24ths or 13 twelfths, if I were to draw it, we'd have a whole bar filled, and then we'd have 1/12. Is 12 twelfths, so let me actually write that. This top one then would be 12 twelfths, and there's one more for 13 twelfths. That's really 1 whole and 1/12. And so when we talk about mixed numbers, which is interesting because a 1 and a 12th are both numbers, so they're just numbers. But what we have mixed is we have wholes and fractions. And so to save us some effort, instead of writing 1 plus a 12th, we write mixed numbers as 1, and then right next to it, we stick the 12th. And there are pros and cons to this notation. Pros, it saves us writing the plus. The con is, if I write, say, AB or 3x, adjacent means multiply. But here, adjacent means add. And so that's maybe one problematic thing about mixed numbers, or something we particularly have to reinforce. But what I want to do is look through some examples, some sample student work to think about mixed number addition and subtraction, because some of these really interesting things are going to come to light. So it says, each of the problems that follow show student work. Discuss it. What is correct and what's not correct? In each case, either complete the work or modify it to make it correct. And so we need to use their work and not just start over. So the first thing we have, we'll look just at student 1, this left side first. What we have is 3 1/4 minus 1 3/4. And so the student said, well, I can't take 3/4 out of 1/4. I don't have enough. So I need to regroup. So let's cancel the 3, rewrite as a 2, and they rewrote it as a 10. So they said that 3 1/4 is the same as 2 10/4. And if we would simplify that, 10/4 is 2 1/2. 1 does not equal 2 1/2. And so there's a mistake in our rebundling. When we cancel out this 3 and bring a 2, we're bringing 1 whole over. So think about when we do standard subtraction. If I do 12 minus 6, when I cross this out, I'm bringing a whole 10 over. So here, I don't bring a whole 10 over, I bring a whole 4. Because 4, that denominator is how many pieces we have. So I don't have just 1, I have 5 fourths. So 3 and 1/4 is 2 and 5 fourths. And we can see that because 5 fourths is 1 1/4, and 2 plus 1 1/4 is 3 1/4. And so when we rebundle with, well, my brain was just like, bam. When we rebundle with mixed numbers, we need to pay particular attention to the size of our whole and the size of the parts within that whole. So once we fix that, 2 and 5 fourths minus 1 and 3 fourths, 5 fourths minus 3 fourths is 2 fourths, and 2 minus 1 is 1. 1 and 2 fourths, or a half. And to check that, we can always add up. 1 and 3/4 plus 1/4 is 2, plus 1 is 3, plus 1/4 is 3 1/4. We're spot on. Now here for student 2, it's the same problem. They cross out that 3, make it a 2, and I saw that they needed 4 out of 4, but 4 minus 3 is 1/4. So they did 4/4 minus 3/4 is 1/4. But we still have this 1/4 here, so let's add on. So that's 2/4. And then 2 minus 1 is 1. 1 and 2/4, or 1 and a half. And so that student was headed down the right track, but we just need to be careful of, it could have very easily gone the route of, and this would be incorrect, so I'm going to use orange. It could have easily gone the route of 4/4 minus 3/4 is 1/4, and 2 minus 1 is 1, and we get 1 1/4, and they could have very easily lost this quarter that was there to begin with. Because when we rebundle this 2 into 4/4, we need to keep track of all 4 of them and not just round it up to the next whole. So thinking about the size of our whole is really important, and the size of our part inside the whole is really important when we think about all fraction addition and subtraction, but particularly mixed number. And so it's important then that we think about when we write, and let me see if I have, I'm going to use this slide and then I'm going to erase it, okay? So ignore the stuff at the top for right now. If I have 2 and 1/3, to write that as a mixed number, we have 2 wholes, which means we have 6/3, plus 1/3, 7/3. Right, so we could work with these as they're improper fractions, is what we call them when the numerator is larger than the denominator. But often we're taught this really rote procedure and we have no idea. Normally it's 3 times 2 plus 1. 3 times 2 is 6, plus 1 is 7, and you keep the denominator the same. And I would say that is not the best way to think of this. The best way is to think is we have 2 wholes, the size of the parts in that are thirds, so 2 wholes is 6/3, and because they're next to each other, remember they're add 1/3. And so I'll keep that. So converting, mixed to improper. Okay, so here we have another problem. There are 2 1/3 cups of milk in a bowl. How much milk must be added to the bowl so that there will be 3 cups of milk in the bowl? So we have a student that starts, we don't have 2, but 2 1/3, so we have 2 1/3. If we add 1/3, we get 2 2/3, and we add another third, we get 2 3/3, which is 3. So we started at 2, and we wanted to get to 3, so we've reached it. So we have 2 more whats. So here the student just says 2 more. Well, we don't add 2 more cups. We had 2 more parts. 2 more thirds, or 2 thirds. So 2 and 2 and a third plus 2 thirds. If I look just at my fractional parts, don't forget there's a plus sign there, not a multiply. 1/3 and 2/3 is 3/3, or 1 and 2 plus 1 is in fact 3. So they were on the right track, but it's not 2 more cups. We have to pay attention to the size of our parts. Another example. There were 5 pounds of apples in a bag. After some of the apples were removed, there were 3 1/4 pounds left. How many pounds of apples were removed? Well, here this student said, well, 5 is just 1 plus 1 plus 1 plus 1 plus 1. So 5 is 1 plus 1 plus 1 plus 1 plus 1. Right? There are 5 of those ones. And each of those can be written as 4/4. And they picked the 4th because that was our fraction of interest in our mixed number. So we have plus 4/4 plus 4/4 plus 4/4 plus 4/4. And they said, well, we were left with 3 1/4 pounds. So let's take away till we have 3 1/4 pounds left. I have 5. If I take away a pound, I have 4. If I take away another pound, I'm at 3. So that's too much. And so I know I need to have a quarter left. And so what's left is 3/4, because now we have 1, 2, 3 1/4. 3 1/4 pounds left means we took out this quarter, or this whole, and this part. So we subtracted 4/4 and 3/4, which means we took out 1 3/4 pounds. And that 1 3/4 is precisely these crossed out numbers in the student work. And the 1, 2, 3 1/4 we're left with is our solution. And so see, think about how we're solving these subtraction problems with very little dependence on the algorithm, right? We're talking through the concepts of quantity and what's happening in terms of rearranging and redefining these quantities. And this is really thinking about how we introduce these sorts of problems, is we use this nature where we talk about, oh, in this real context, I could see that doing this, right? And so thinking about how to do that, we don't have to find common denominators in the same way. It's not that we aren't, because we did. When we had our 5, essentially what we did was found a common denominator. That 4th, because that's what our 3 1/4 was given as. And so the things are happening, but in ways that are much less procedural and much more conceptual. We have to think about the meaning of what is happening. So here, add 2 2/3 and 1 2/3. And then the mistake we're going to see here is a really common one. So 2 2/3 plus 1 2/3 is 3 4/6, because the fraction part is 4 out of 6. So this is 2 2/3, 2 2/3, and this is 1 2. Well, just kidding. Is 1 2/3. So to combine them, we can combine our wholes, 3. And then we have 2/3 and 2/3. So the mistake the student makes here is they change the part. Or rather, they keep the size of the part the same, but they change the whole. So this is a whole. That's the whole. It's broken down into 3 equal pieces. If what this showed was 4 out of 6, So let me pick a different color. 4 of 6, really, right, looks like this. But what happens when we write this as 4/6 is that's saying this is the whole. And this whole is twice as big as the original. And so it's not that we have 4 of these 6, because remember, each one of these, I'll color that in just for clarity, is 1/3. So we have 1, 2, 3, 4 of those thirds. We have 4 thirds. So we have 3 and 4 thirds. And so the thing to track when you're looking at student work, and even catching in our own work, is when we have these pieces, are we accidentally changing the whole when we give our final answer? Because, right, we see where this student sees what's happening, right? The student sees, let me get a highlighter because that'll be a little bit better than using pen. They see those 3 boxes, 2 are shaded and 1 is not, and they see these 3 boxes and 2 are shaded and 1 is not. And they're like, well, there are 4 of the same size, or there are 6 of them that are the same size and 4 are shaded. So 4 out of 6. But if we think about our fraction addition, and so let me write a little bit over here now. When we would add this, first we would take the 2 from here, and then we would take the 2 from here, fill this one up completely, so that's a 1 and a third. And so now we see where that 4/3 is, right? That 4/3 is really just 1 and 1/3, which means that 3 and 4/3 is really 4 and 1/3. But by breaking that step down and showing that extra fraction addition of 2/3 plus 2/3 is 4/3, I think really helps us to see that unless we're changing something, this is my whole. And I have one whole and another third of a whole. I do not have 4/6 of a whole, right? We don't want to look at it that way. So again, thinking about fraction, addition, subtraction, what is our whole? What's the size of the part of each whole? And how many of each of those size pieces do we have? Those are the 3 things we need to keep track of when we're working through fraction, addition, and subtraction. So decimals. So I told you that decimals are really just special fractions because they're connected to our place value, which means that when we do decimal addition and subtraction, we can use place value facts to get to our solutions. So first, if we have decimals and we have to subtract or add them, we already can know how to add and subtract fractions, so we can just put them in fractional form. So say 2.16 plus 1.73, or 2 and 1600ths and 1 and 7300ths, which we can write in expanded form, right? So we had a little bit of practice doing expanded form earlier this week. Expanded form. And now we have commutativity and associativity. So what we can do is we can put our wholes together, 2 plus 1, plus, and now we have 1/10 plus 7/10 plus 6 100ths plus 3 100ths. So that's by commutativity and associativity. Right, we have 2 plus 1 is 3 plus 8/10 plus 9 100ths, which means it's 3 and 8900ths. And of course I have a decent looking one hiding in the background, 3.89. And so we can convert to expanded form and go. But that is a lot of work. Like, that added so many written things between my start and my ending point. Because sometimes we care about efficiency. Something that's really great about doing decimal subtraction addition this way is it connects to place value and it draws on the big idea of place value. It connects to the concept of what does 0.16 means. Well, it means 1/10 and 6/100ths. And 0.73 means I have 7/10 and 3/100ths. And so I can add those to the other ones. We can add like denominators because they're same size pieces, and we get our final answer. But that's not the most efficient. And so before we move to the efficient addition, I want to give you another representation, and these are called decimats. And so if you look at your homework, there is a specific problem where I say, use decimats to find the, I think it's sum or difference. And so there are lots of ways you can do this, but it's really essentially a simplified version of, or rather a paper version of the base 10 blocks. And so I'm going to give you some definitions. This whole, this largest rectangle, one that looks roughly like a piece of paper, that's one whole. This small piece here, one of these slightly smaller rectangles, is a 1/10. A 1/10 of a 1/10, we already talked about, is 100th. And then that one over there on the left has a really tiny square. And so I'm not sure exactly where I should draw that. I'll put it here. And that's my 1,000th. And so when it comes to modeling decimals, we can use a decimat either with whole numbers or only fractional parts. So let me pick two colors. 0.422, that's 4/10. So 1, 2, 3, 4/10. 2/100ths. 1, 2/100ths. And 2/1000ths. And then another number, another color, orange, 0.253. It's 2/10. 1, and because I used that corner one, I'll just fill this one in, 2. 2/10. 5/100ths. 1, 2, 3, 4, 5/100ths, and then 3/1000ths. And so since we're looking at the sum, we care about the total amount of each. So we have 1, 2, 3, 4, 5, 6/10. So I'm going to write this as a fraction, and then we'll go back to the decimal. We have 6/10 plus 1, 2, 3, 4, 5, 6, 7 100ths plus 1, 2, 3, 4, 5 1,000ths, which means we have 0.675. And notice the decimat helps us see we can just add by place value. 2 plus 3 is 5, 2 plus 5 is 7, 4 plus 2 is 6. And so decimats are another way to reinforce the meaning of decimal in terms of area of a whole, and decimal addition, which is the joining, or you could use subtraction too, right? You could cross them off instead of adding them on. You could even use red and blue and use your positive and negatives, right? And think about your zero-sum pairs. But again, this is great until we have thousands, or, I mean, there are ways you could, in theory, keep dividing, or if you had it on a computer, right, you could zoom in infinitely and keep drawing. But there's a point where this isn't the most efficient. So we start to get there by thinking about place value. And notice the really close connection between this and the previous, where it starts to point out, oh look, if we have wholes, tenths, and hundredths, we can just add down by place value, just like we added ones, tens, and hundreds in addition of whole numbers. So if we have 2.16 plus 1.73, we have 2 flats, which here is standing as our whole. We have 1 long and 6 units. And then we have 1 flat, 7 long, and 3 unit. And we can do any number of our regrouping strategies where we can split, say, this flat. We can split one of these flats into 10 more longs. And then what we do is we say we have 6 units minus, we're adding. We're not even subtracting. Look at that. I'm doing all of this work because we have to rebundle to subtract. And we're adding. 6 plus 3 is 9 100ths. 1 and 7 is 8 tenths. And 2 and 1 is 3 wholes. 3.89. But right, that's exactly how you would demonstrate that subtraction problem. And maybe just for the sake of completion, let's go ahead and do the subtraction problem now. So 6 minus 3 is, so let's do minus. 6 minus 3 is 3. 6 take away 3 is 3. 11 minus 7 is 4. And 1 minus 1 is 0. 0.43 should be the difference. We can check that. 1.73 plus 0.03 is 1.76. 1.86960616. Or we can think of this in terms of hundreds. 173, 176, 186, 96, 206, 216. We're good to go. And these are some of those mental math strategies we briefly mentioned previously. And so the most efficient, after we have place value understanding, because we need place value understanding before we move on to standard algorithms. When we look at this, we have 2.16 and 1.73, and suppose you are going to do subtraction again. Let's subtract. 6 minus 3 is 3. One of those means we now have 11 of these tenths. We're left with 4, 0.43. And so this comes from Engage New York. This is a place value chart, and so you can very easily line up your numbers, use them to practice. And eventually we get to the standard algorithm, which just says 2.16 minus 1.73, 3, 1, 11, 4, 0. Right? Because when we're doing place value, or when we do the standard algorithm, what we're looking at is efficiency. And efficiency is useful, but also if you want to be really efficient, you can just use a calculator, right? And so that, I think, gives us a nice introduction to addition and subtraction of fractions and decimals. So that's where we are so far. I'll just go back to this one so there's something other than nothing on the screen. And what we're going to do, this is where we'll end the material for quiz 3. So because day 4, which is fraction multiplication and division, is technically Thursday's video, I don't want to include that on Thursday's quiz. And so quiz 3 material will be last Thursday's video up through today. And so for the rest of the week, I'll have one more video to post, which is on multiplication and division of fractions and that material. And then we don't have a quiz next week because a week from tomorrow's video is our final exam. And so what I'll do, the final exam will cover all of the material in the course. But this material from today and then next week 4, Monday, Tuesday, Wednesday, you won't have seen on a quiz. And so I'm probably going to give a substantial portion of the final to that material, to fraction, multiplication, division, and to some of these other concepts that we're going to unpack next week. And so I want you to know that that's coming. The final exam will be cumulative, but it will emphasize material after quiz 3. There will be stuff from everything up to that because all of this is so incremental, right? The set definition from day 1, which didn't feel useful, we're still talking about today, right? And all of these things, all of these restrictions and formalities, we're talking about what happens if we change it in this way. So that, I think, gives you an idea of what's happening, and I will see you for our next video tomorrow. Bye, everyone.